So today we're going to be talking all about acceleration, deceleration, change of direction, multi-directional movement analysis, and how we think we could potentially do a better job of it in team sports. So just to kick off, my name is Jo Clubb. I'm a sports science consultant. I previously worked for a number of years in professional team sports with Chelsea, Brighton, and then in the US with Buffalo Sabres and the Buffalo Bills. I'm joined today by Andrew Gray, and Andrew and I have known each other for quite a long time now, and I'm really excited to share some of his thinking and get into some of the amazing work that he's been doing in this area. So, Andrew, if you just want to introduce yourself and share your background and then what you're doing day to day right now as well.
Joe, thanks for having me. It's exciting to chat to you anytime. My background essentially as a high performance practitioner. I worked in professional sport in Australia for almost 25 years. I'm a physio, strength coach. I'm old enough to have been around when sports science really got going, which is quite a long time ago. And I was also old enough to be around when tracking devices got going. So as soon as tech started to land in sport, I was looking, but was searching for more immediately. And with a real do-it-yourself kind of attitude, I did it myself. And I've subsequently built 3 software programs. One, a tracking device software program called ADI, an IMU-based machine learning activity classifier for a large military organization. And I'm also involved with a company called Sportscientia with some in-tube technology measuring gait. So these days, I'm not face-to-face with teams anymore. I live in Australia. I've moved down to the bottom of the beautiful South Island of New Zealand and focusing more on consulting, building software programs, and talking to you.
Yeah. And we should say that, so ADI, Athletic Data Innovations, you've been doing this a while because, as you said, you felt that the tracking data or the GPS data that you were getting wasn't representative enough of the demands of the game. And back, 10 plus years now, when I was at Chelsea, we worked together under Nick Broad, who you connected with. And very early on, you were giving us greater insight. But I think now, having spoken to you quite a lot recently in terms of as well how you've further developed the system and what it can do now, makes it really valuable. So I'm really excited to share this and help you educate us as to some of the limitations in how we try and capture these movements. In team sports, we know that these multi-directional movements are important from an injury perspective. They're often involved in the mechanism to injury, and also important from a performance perspective. So one study I've seen analyzing the Premier League movement demands from a few years ago showed that the second most frequent action preceding a goal was a deceleration. The third most frequent was a cut, so a change of direction. So we know they're important for performing and for injury. But we've also long known that there are issues with how we currently collect it. Some of these issues I've written about myself. I've written a post on my blog on Global Performance Insights, as well as an article for Sportsmith for Rob Pacey. Early on, Martin Bouchard published an article saying it was time to slow down because the reliability wasn't there. The technology has moved along now and is improved, but we still face issues around, what thresholds do we use? What dwell time, what minimum effort duration do we use? And a paper came out recently that showed that we're probably underreporting accel, decel based on that. Another thing is the mirroring between why do we think about accel and decel the same? Why do we use the same thresholds when actually they're quite different demands? So those are some of the issues that I have seen, but I think you in recent times in our discussions have opened my eyes to a whole other host of ways that we might be overlooking these kinds of movements. I'd love for you to kind of explain some of the issues beyond what I've just described in how we are trying to capture these kinds of demands.
Yeah, sure. And I mean, when we first met back in Chelsea, I think that's almost 15 years ago now. It's close to that. It's actually a really long time ago. And yeah, ADI did start because I wanted answers for myself, for the team that I was working with. So I was coming at it from a practitioner's angle. And yeah, the professional sports world is pretty small, let's face it. And ADI really became a business when other teams started calling up and saying, hey, we've heard what you're doing. Can we have a look at that too? And that's the way ADI has operated for the last 15 years. It was a tool for me that my friends also used at other teams, which is great. It helped, it can be connected to practitioners in other sports, different codes all around the world. It's been a really good educational experience for myself, and probably prevented me from being isolated in one sport and in one team. It's probably kept me in pro sport for a lot longer than it should have. Now that I've moved away over the last couple of years, I've had an opportunity to address the things that were bothering me that I didn't have time to fix. And all those points that you mentioned were great points. And, let's face it, used to keep me awake at night about thresholds and how we should be measuring things and are we doing things the right way. Most of your subscribers and people listening to this are going to be working with athletes who play multi-directional sports. They all have multi-directional movement profiles. We know that changes of direction, you would set higher heart rates, higher blood lactate concentrations, higher oxygen consumptions than linear movement of the same speed. We know that. We know that multi-directional movement has a cost. We know that our athletes play multi-directional sports. Yet, as a profession in the 15 years, we haven't progressed quickly enough into understanding multi-directional movement analysis for our athletes. And that's what has bothered me for a long time. ADI is always focused on measuring as much of the movement spectrum as possible. Number one, not letting things fall through the cracks, seeing everything so that we can get a more complete understanding of the movement demands. If we know the movement demands of matches, we can more effectively plan training. We can more effectively rehabilitate athletes. We can understand where the risk lies. We can categorize our drills better. We can put together better training sessions, better training weeks, have less injuries and perform at our best. That's the theory, right? That's what we all try to do. So that's where I've been coming from. And I think what we're really going to be talking about here today is the fact that acceleration and deceleration, whilst they do tell part of the picture, an important part of the picture, they don't tell the entire picture. We're missing the acceleration associated with changing direction. And I don't think it's our fault. I think tracking companies gave us speed when they first landed and started providing data to us. And we decided that a change of speed was an acceleration. An increase in speed was an acceleration. A decrease in speed was a deceleration. But that's not what we learn in physics at university. And that's not what really describes multi-directional movement. That's what we're missing.
So this confused me at times, right? Because it's so ingrained in us. You can be accelerating in that way. But I think getting into now the acceleration that we've been missing, acceleration, as you say, associated with change of direction, is important. And it's maybe going to take a couple of different examples and ways to describe it, because as I said, it's so ingrained. It's taken me a few different discussions to wrap my head around it. So can you help illuminate some of this for us?
Sure. And I guess where it really begins is the difference between speed and velocity. So we were given speed, but we've started to call that velocity. And we tend to use the term speed and velocity interchangeably: max velocity, velocity bands, velocity thresholds. Speed is a number. Speed just has magnitude. And speed really is the number associated with velocity. It's called a scalar quantity in physics, means it's just a number. Velocity is a vector. So velocity has both magnitude and direction. It has two qualities. Speed is equal to the magnitude of velocity, and bearing, or the heading, where we're headed, is the direction of the velocity. And velocity is a vector. The way we think about those in mathematics is it's an arrow. In a Cartesian plane, it's an arrow that has a beginning and an end, and the arrow tells us which direction it's heading. The length of the arrow tells us the size of the velocity vector or the speed. So by definition, when we change velocity, we're accelerating. When we change displacement, we have velocity. Displacement, velocity, acceleration, they're all vectors. They all have two parts that are required to explain them: magnitude and direction. So if to accelerate, we have to change our velocity, it doesn't mean we just have to change our speed. We can change our speed or our direction of our velocity, and we're accelerating by physics definition, by first principles physics. Therefore, if we're running at a constant speed, but we're changing our direction, we're accelerating, and we're missing that. Because we would say that there's no change in speed, there's no acceleration. if we change our speed and change our direction, we're only considering the acceleration due to the change in speed at the moment, not the change in direction. So therefore, if we think about the shuttle turn, for instance, say a 180-degree turn, it involves someone entering a turn and decelerating, slowing down. Then there's a turning phase. Then there's a re-acceleration once they've made their decision to head off in another direction. We're measuring the deceleration and the acceleration associated with changing the speed, but we're not measuring the acceleration associated with the turn. Now, the way to kind of think about that is, we're accustomed to that concept of increasing speed is acceleration, decreasing speed is deceleration, but we're not accustomed to considering direction change acceleration. We know from physics that if you change your velocity, you're accelerating either the magnitude or the direction, like we spoke about. And then you experience this acceleration yourself when you turn the corner in a car. That's probably the thing that everyone can go, oh yeah, I do know that I get flipped to one side. What you notice is a sideways acceleration because you and the car are changing direction. And the sharper the curve or the higher the speeds, the more noticeable this acceleration will become. That's what we're not measuring. And that has a profound effect on the way we quantify match demands, measure load, quantify a rehabilitation session or a drill, so on and so forth.
Yeah. And that example for me of being in the car that stays at the same speed but changes direction and you get thrown across that's the analogy that's hit home for me. Obviously, we're not saying to ignore or remove all the speed change acceleration, but that there is a vast component that we've been overlooking through no fault of our own. And clearly anyone who thinking about any kind of team sport, football, Australian rules football, basketball, ice hockey, American football, when we think about the change of direction, the change that this kind of acceleration will obviously be a massive component of the game and therefore of understanding all the applications you listed, understanding match demands, training prescription, training analysis, and therefore, of course, rehabilitation. So once we wrap our heads around this direction change acceleration, suddenly, it's been enlightening for me to think about, oh yeah, well, if we can now capture it, as you're going to demonstrate, then that unlocks a lot more information to use with our athletes.
Yeah, you use some great examples from sports like AFL, where players often change their trajectory or their direction at moderate to high speed, evading an opponent, tracking the ball, really difficult things to do, like running the curve in a 200-meter race. Why that's such a difficult thing to do is to change direction at high speed. And, it's no surprise that we notice athletes running a 200-meter bend leaning towards the center of the track. We notice people change direction, leaning towards the center. The same way you'll lean in your car, turning a corner in order to overcome that acceleration. Evidence that there's an acceleration occurring. There's additional force having to be applied. Ice hockey is another fantastic example there. Athletes traveling at moderate to high speeds and changing trajectory requires additional force. Whenever you're applying an additional force, you do that to accelerate a mass.
So, of course, we do know, as I mentioned a bit earlier, that there has been a real shift in attention to these kinds of movements in terms of decelerating change of direction. We have seen, of course, Damien's work leading the way in some of the deceleration work. We've talked about the textbook coming out now, which is the first time multi-directional work has been so emphasized. So there is this real interest in this acknowledgement of the importance of it. But as you're highlighting then, we have been overlooking this direction change acceleration portion of it. So why to you is that important now to pause and reassess and try and capture that portion of acceleration?
It's a really good question. And I think, every process is a journey, and the whole tracking athletes has been a journey. And at this point in the journey, we're all realizing how important it is to start quantifying multidirectional movement because we train multidirectional athletes. Now, the accelerations during changes of direction are the highest accelerations that athletes make. The accelerations measured in high angle direction changes at high intensity are higher than decelerations, linear decelerations, and linear accelerations. They're the highest acceleration, highest force movements. That's why people get injured during doing those things.
Mm.
That's why they're the last thing. It's one of the last things you really add into rehabilitation programs when people are ready. That's why they're huge events in sporting matches. That's why they're critical moments. That's why our best athletes are so good at those things. They're the most technical things to do, and they involve the most force. And we need to be measuring them, because if we're missing them, then any metric that we use using an incomplete version of acceleration, there's cracks in it when things are falling through the cracks. And the things that are falling through the cracks are the highest force movements that we really should be capturing.
Yes, the irony there, right? They're the most critical, probably, again, as we said, both performance-wise, injury-wise. We've long searched for one simple number that represents training load, even though we know there's so much complexity, especially in team sports. And depending on your supplier, some people might look to player load, some people might look to HMLD. And of course, pros and cons to all those total load variables. But as you've kind of highlighted to me, none of them currently are considering this portion of the demand, which, as you say, is arguably the highest, most intense demand. And certainly some of what I've seen from your system in terms of trying to quantify load for an athlete and then also break it down into its component parts. That's ideal. We've had a lot of limitations in doing that in the past, but I'm genuinely excited with what I've seen from how you're approaching this now.
They're great. So am I. And there are assumptions that we make. We have, talking about a GPS device located in the upper thoracic spine. Our assumption is that represents the movement of our center of mass. And it doesn't. That's an assumption that we're making. There's additional movement of an upper thoracic based device that we don't want if we're looking at the movement of the center of mass. And there's also some things that we're missing. So there's the first assumption. But like you said there, looking for that whole number, in that whole number, are we talking about energy, or are we talking about work? They're two different physics schools of thought. Is it about, energy, metabolic energy, or is it about mechanical energy, our mechanical output or our metabolic cost? Yes, we've been searching for all those things all along, but we've got to remember that at the moment, specifically talking about tracking devices and GPS devices or LPS devices, we're really only able to measure what is a surrogate for the center of mass. So it's telling us how we're moving our center of mass, which really is only talking to us about our external work. Our complete work, or our complete cost of movement, is the movement of the limbs and the movement of our center of mass. We can't measure the movement of our limbs unless we're attaching something to our limbs, which we're starting to do with in-shoe devices and those sorts of things, or with computer vision. We can measure the movement of the limbs. So yeah, finding that one number is tough, and there's a lot of different ways you could approach that. But what we can do is make sure that we're not missing any of the movements that matter. And at the moment, we're missing the movements that particularly matter the most. So given the device that we've got and the limitations that it has, or optical tracking has, and all those sorts of things, I think the best we can do with what we've got is to not miss any movements. And that starts with the correct measurement of complete acceleration by adding the missing piece. Yeah.
Yeah. And I think it is worth noting there that we've talked a lot more so about GPS, but as you said there's optical tracking, there's camera systems, RFID. We all know that this technology is rapidly increasing or evolving. How you work is to be technology agnostic. So you can take in that data. We're not talking about replacing a GPS system or changing to a specific system. Whatever system people are working with, your system works to take that data to then run through your system to then give them a dashboard and the specific metrics that you're talking about, regardless of who their provider is.
Yeah, that's right. ADI has never been a hardware provider. That requires too much of an outlay, and it's too complicated for me. Basically, ADI needs X, Y, and time. It needs where you are and when, and that's it. And the ways we can get X, Y, and time are from GPS devices, LPS devices, optical camera systems. Any X, Y, and time is pretty much all ADI needs for its acceleration methodology. GPS devices obviously do include IMUs. They've got an accelerometer, a gyro, and a magnetometer inside them, and we do use those for other purposes within the program, but we don't rely upon those for this acceleration methodology. There's lots of ways you can measure things, and an accelerometer gives us acceleration, but we know there's issues with that acceleration and there's drift. So unless we're going to be continually fixing calculations up from an IMU in some manner, they're going to drift, which means we can only make really short decisions and really short snippets before they get inaccurate if we're going to be calculating things. Whereas our ability to measure location and time is much, much better than it was 10 years ago, and it's going to continue to improve. So I guess ADI has been ready with this methodology, waiting for the tracking systems to catch up. I think that time is approaching.
Yes, you've always been ahead of the curve, for sure. You are very kindly going to share a bit of a demo next. And for me, I think this is definitely worth watching because it really illustrates what we've been talking about, but the potential, I think, for ADI to solve some of these big issues that we've been talking about. If people are interested in chatting with you more after watching that, how should they get in touch?
Yeah, I mean, other than contacting you, Joe, and you putting them in touch with me, the best place is probably LinkedIn for me. I tend to use social media for chasing where the snow's good and, snowboarding videos and multi-sport races and that sort of thing. So LinkedIn's probably
The important things.
Yeah,
The
that's
important
right.
thing.
Yeah.
Okay, so Andrew Gray on LinkedIn, or absolutely, they can get in touch with me through Global Performance Insights or on social media. I can put them in touch with you. Thank you for sharing the science behind it now, and we'll get into the demo.
As we discussed earlier, regarding acceleration, it's time we change direction. Traditional tracking methodology is presently using an incomplete form of acceleration. The fundamental difference between traditional tracking methods and ADI metrics are shown here. The left side of the screen shows how traditional metrics view multidirectional sports. The way ADI looks at multidirectional movement is shown on the right side of the screen, measuring every change in speed, but also every change in direction, resulting in complete acceleration that enables the quantification of multidirectional movement. The most important question we must ask ourselves is this athlete accelerating? He's running at a constant speed, but he's most definitely not running at a constant velocity. And it is this distinction that we'll now discuss in more detail. As we discussed earlier, speed is a scalar quantity. It only has magnitude. It is just a number that represents the magnitude of velocity. Velocity is a vector quantity. It has both magnitude and direction. Now, most importantly, acceleration is also a vector quantity. It is the rate of change of velocity. So if we change either our speed or our direction, we are accelerating. Now for a real-world example. Two athletes running side by side on a football pitch start together at the 6-yard box, and they build up speed till traveling at 6 meters per second, still directly side by side. As they approach the center circle, athlete 1 continues at 6 meters per second towards the other end of the pitch. Athlete 2, on the other hand, begins to follow the center circle, an approximate 9-meter radius, without changing speed at all. They are still both traveling 6 meters per second. Traditional tracking methods will tell us that these two athletes are doing the same thing as each other. No acceleration, same accrual of high-speed running distance, no change to HMLD. But this is incorrect. Athlete 2 is accelerating. We are missing this point, which has profound effects on the way we measure the cost of multidirectional movement. Now, on the top left of the screen, we see a speed graph for an athlete tracing a center circle, plateauing at approximately 6.5 meters per second, a maximal effort for this athlete on this trajectory. We see the speed and traditional acceleration shown below the graph. Note that the traditional acceleration approximates 0 throughout the constant speed portion of the video. In the top right, we see the direction the athlete is heading, or their bearing, and below that, 2 gauges that show the direction of the athlete's complete acceleration. In the bottom left, we see a gauge that displays the ADI acceleration of the athlete, showing 3 components: the complete acceleration on the top, the direction change acceleration in the middle, and the speed change acceleration at the bottom. Remembering that traditional tracking methods will register no acceleration whatsoever for this athlete once they reach a constant speed, this is alarming. The complete acceleration approximates 5 meters per second throughout the constant speed portion of the clip as this athlete moves as fast as possible around the center circle. Now, this is a high power task and a near maximal acceleration for this athlete. Okay, so here we have the same plots and same gauges, same athlete, and another near maximal effort. However, this time the athlete is tracing a 7-meter radius circle, not a 9-meter radius circle. Here, he can only maintain a constant speed of approximately 6 meters per second, yet his complete acceleration once again reaches 5 meters per second, a high power movement and a near maximal effort. Traditional acceleration methods once again record 0 once the athlete reaches a constant speed. Lastly, the circle has been reduced to a 5-meter radius. Now, the athlete can only maintain a constant speed of approximately 5 meters per second, but once again, their complete acceleration approximates 5 meters per second, another near maximal effort. These clips demonstrate that by using the ADI acceleration methodology, we are able to build a complete picture of the acceleration associated with multidirectional movement. As the inputs for metabolic power calculations are speed and traditional acceleration, they are flawed and underreporting what are perhaps the most important movements made on the pitch. I must credit this image to Johnny Bloomfield and my good friends at what was previously Prozone, generated during our previous collaboration. This image shows an athlete performing a 180-degree maneuver to the right. A maneuver is defined as a movement or series of moves requiring skill. We know that a 180-degree turn to the right involves 3 main movement modes. 1, a deceleration, 2, a change of direction to the right, and 3, an acceleration. There are countless ways that an athlete can perform this maneuver: a straight line deceleration, a rapid turn followed by a straight line acceleration, or an arced deceleration that smoothly becomes the turn phase followed by an arced acceleration phase. A lot of this depends on the strength and skill level of the athlete as well as the approach speed of the maneuver. Now, the ADI platform automatically detects each and every maneuver, linear or multidirectional. It separates them into their respective categories as well as their individual movement components. It quantifies both the speed change acceleration and the direction change acceleration, as well as providing a clear understanding of the strategy used and its level of performance. At ADI, we call this complete acceleration, now making it possible to understand for the first time the mechanical cost of all multidirectional movement. The main point of this software is to try to save people time, to really try and accelerate the path to insight. So making things easy so that people that are using tracking devices and trying to improve the performance of athletes can start focusing on other things. If this explanation provokes your interest and you'd like to learn more about how ADI can assist your team, I'd be more than happy to provide a complete demonstration of the actual platform. Just get in touch. Thank you.